today is our introduction to polyatomic ions. So we need to understand what the word polyatomic ions mean. So the first thing we're going to do is we are going to figure out what the word ion means. Who could tell me what ions are?
Something that is charged negatively or
Perfect. Something negatively or positively charged. All right, so we know what an ion is. Do you guys know what this prefix poly means? You might have heard of like a polygon.
many like sides.
Perfect. So there's many or multiple of them. So many or multiple. And that's what the poly means. And then we have this word atom. And hopefully you guys remember atom from last semester because that is all we pretty much talked about for the majority of our class. So hopefully that does ring a bell. When we're talking about polyatomic ions, we are talking about atoms that have charge, but there are multiple atoms already bonded together with a charge. So there are multiple atoms bonded together with a singular charge, or just one charge for all the atoms that we bond together. But if you remember from when we talked about ions in general, and we talked about when we put them together, we wanted to make sure that our bonds don't have a charge, which is why these things are so important, is because there are multiple atoms bonded together that still leave a charge, which means we have to bond them with something else for them to be stable or to be happy, for everybody to fill their octet rule. So we have ions, or multiple atoms that are bonded together with a singular charge. These ions, what kind of bonds do you think they're going to form? Are they going to form ionic bonds or covalent bonds?
Ionic.
Ionic, because we have ions. If we remember, ionic bonds have a charge, and we have to worry about those charges because the electrons get transferred. In covalent bonds, we don't worry about charges because we're sharing our electrons, which means that the charges do not affect us in any way, shape, or form. So we only worry about ionic bonds for these polyatomic ions. And this one is a little bit different than polyatomic ions. Just a refresher for all you guys, just to remember, why do some elements have Roman numerals? So first, can you guys answer me, which type of elements have Roman numerals?
Transition metals.
The transition metals have Roman numerals. And those Roman numerals, what do they tell us? They tell us anything? Let's look at our periodic table. We know our transition metals, those elements in that middle section, 3 through 12, for groups 3 through 12, those are the ones that have Roman numerals. Why are those elements different than all the other elements in all the other groups? Anything in particular that we don't know from those elements that we have to figure out based off Roman numerals?
If they're positive or negative.
Not if it's positive or negative, but I like that idea of charge, those Roman numerals, because all those elements are going to have a positive charge because they're all closer to that side of losing those electrons. They all want to get rid of theirs. But those Roman numerals tell us how many valence electrons that element is willing to lose or what positive charge they're going to have. So if you see a Roman numeral 2, that means they're going to lose 2 electrons, meaning they're going to have a positive 2 charge. So again, those Roman numerals tell us how many valence electrons the element will lose or what charge they're going to have. So we're going to watch a video and then I'm going to let you guys work for about 2 minutes to try and make observations and then identify if the reaction we watch is endothermic or exothermic. So before we do that, I do need you guys to remember what the difference between endothermic and exothermic are. And that was the last thing we covered in the semester, last semester. Can anybody refresh my memory as to what endo or exothermic reactions are?
Exothermic releases the energy while endothermic gains energy.
Exactly. So endothermic reactions, we absorb or gain energy or heat. Exothermic reactions, we release energy or heat. So remembering it in terms of like endo looks somewhat like enter, so heat is entering the system. Exo looks like exit, which means heat is exiting our system. So just remember that when we do watch this video of this reaction with a polyatomic ion, specifically potassium chlorate. And we'll talk about polyatomics more in just a second. Let's watch this video. All right. Just gonna restart. All right.
This is a boring old gummy bear. And this is what happens when you drop it into boiling potassium chlorate. Whoa, that was awesome. But we're VAT19, and this is the world's largest gummy bear. So...
Did it freeze on you? Hopefully you get the gist of it. Same thing for another probably a couple seconds. If you guys want to watch it again so you can make your observations, go for it. Take about 2 minutes and make observations about this video, and then we're going to come back and talk about those observations as a class. So make your observations. Alrighty. So, all right, ladies and gentlemen, what observations did we make about that video?
Once the gummy bear was dropped, there was a releasement of energy slash heat.
All right, so we saw the gummy bear drop, and we saw energy being released or heat being released, and we saw that being released in what way?
An exothermic way.
All right, it was exothermic. And what do we see to make sure that we knew a reaction was happening? What did it look like?
Explosion.
An explosion. An explosion happened. And so we know that we saw like that explosion, we saw that heat or energy being released, which told us that a reaction happened during this, and we know that it was an exothermic reaction. So this is one of the many examples of polyatomic ions forming this reaction. So you guys saw a polyatomic ion, specifically potassium chlorate. And so if we talk about this, potassium, is potassium a polyatomic ion, or do we get it straight from the periodic table?
Polyatomic.
Potassium's a polyatomic ion? Or do we see it on the periodic table?
We see it.
We see it straight from the periodic table. Potassium, it's number 19. It's on the periodic table. We don't have to look anywhere for it. Chlorate kind of looks like chlorine, except for there's that funny ending that you're going to see. So that ending is one of the polyatomic ion endings that we're going to look for. So if you see either of these two endings, ATE or ITE, that's going to tell us we're looking for a polyatomic ion rather than looking for an element from the periodic table. If it comes from the periodic table, what ending would it have if we pulled it from the periodic table and we put it in an ionic compound?
IDE.
Well, you'd have IDE as our ending. And so the difference when we're looking at the names, it's going to be that ATE and ITE versus the IDE. Now, in order to figure out the polyatomic ions, I'm not going to have you memorize anything. We're going to get a second chart. So this chart we're going to find on our Canvas page, and it's not in the assignment because putting it in the assignment usually means that people lose it. So instead, if we go to the home page and we go to class resources, when we open up those class resources, number 5 says polyatomic ion sheet. And we're going to see every ion that we can worry about. We have ions, we have those Roman numerals for the cations. Anything that we're looking for would be on this sheet, or mostly everything that we look for is going to be right here on this sheet. So I would say download this to your Notability, put it in a picture form, whatever way you're going to be able to find it later so that you can use this, because this is going to be super important for you to be able to use throughout this entire unit. I have mine downloaded to Notability. So if we look, we're going to go through some examples together of naming, going from name to formula and going from formula to name. So this first one, potassium nitrate. Potassium, is that an element from the periodic table? Can we tell me that element symbol?
Yes.
What is it?
K.
Awesome. We have K here. Nitrate. Now remember, we have to look at the ending. Is that an element from the periodic table, or is that on our polyatomic ion sheet?
Polyatomic.
This one's a polyatomic because of that ATE. So we go to the ion sheet and we look for nitrate. I'm just going to keep scrolling. If you find it, let me know.
NO2-1.
All right, so you just actually helped me explain the next set of information. Look closely. So we have two options. We have NO2 and we have NO3. There's one small difference, and that is this wonderful I versus this wonderful A in our name nitrate versus nitrite. The only difference which changes our entire compound. We could have NO2, which is nitrite, or NO3, which is nitrate. So let's double check our question. Are we looking for nitrite or nitrate?
Nitrate.
Nitrate, that ATE, which means we want NO3 with that -1 charge. So I'm going to put my NO3 with a -1 charge. Now remember, we don't want charges in our final compound, but we do need to know the charge of both the cation and the anion. So we need to know what charge potassium is going to have. Or in other terms, we need to know how many valence electrons potassium is going to lose. So it's stable or so it's happy. So if we look at our periodic table, potassium is going to lose how many valence electrons so that it has a full valence shell. So it's stable.
1.
Just the one. Perfect. It has one valence electron to lose. So which means if it loses one valence electron, what charge does it have?
+1.
+1 charge. And now we need to make sure our charges cancel out or add up to 0. Do our charges add to 0?
Yes.
Then we are done. Our final formula then becomes Kn NO3 all together. Any questions on the first one?
We don't add the +1 or the -1.
Nope, just like our formula. So if we had something like Na with its +1 charge and Cl with its -1 charge, when we wrote that formula, it just became NaCl. Just like that, because in an ionic compound, we don't want charges in the end, which is why they have to add up to 0. Just like that, we have to worry about ours for these the same way. We're going to look at that next one, lithium sulfate. We're going to do this one together too. So let's identify, is lithium a ion from the periodic table, or is it going to be from the polyatomic ion sheet?
Periodic table.
All right, what's my element symbol for lithium?
Li.
Li is wonderful. What about sulfate? Is that periodic table or is that ion sheet?
Ion sheet.
Ion sheet because it's got that ATE. All right, so let's zoom out. Do we see sulfate?
SO4.
SO4 with that -2 charge. Perfect. All right. The last thing we need to know before we can write our formula is what the charge on lithium is going to be.
+2.
So let's double check that one. So let's look at our periodic table. Where's lithium? What element? What's the atomic number?
Atomic number 3.
Atomic number is 3, which means how many valence electrons does it have?
1.
It just has one valence electron. So in order to become stable or happy, it's only going to lose one valence electron. So it's only going to have a +1 charge. But that does cause us an issue because now our charges, do they add up to 0?
No.
They do not. So how could I make this a formula that would end up giving me a charge equal to 0?
Adding another lithium.
Bringing in a second lithium with another +1 charge means that now my charges will add up to 0 and I can write my formula. Li2 for 2 lithiums, SO4. Any questions on that one? All right, then you guys go ahead and do copper 2 iodate, or iodite, sorry. Do copper 2 iodite, the third one. I'll leave this up here so you guys can look at it. Go ahead and take about 2 minutes to do that one on your own, and then we'll come back together as a class. All right, ladies and gentlemen. So the next one, that was copper 2 iodite. Can anybody tell me what the element symbol for copper is?
Cu.
Cu, perfect. What about iodite?
IO2 -1.
IO2 with a -1 charge, perfect. Last but not least, can you guys tell me what the charge on copper is going to be?
A +2.
It's a +2 charge. Where we get that +2 from?
The Roman numeral.
The Roman numeral tells us there are 2 valence electrons that it's going to be willing to lose. And so that gives us a +2 charge. Do my charges add up to 0?
No.
They do not. So how could I make them add up to 0?
Adding another iodide.
Adding another iodide. So I add another IO2 with a -1 charge. Now do my charges add up to 0?
Yes.
Yes. So now I write my formula. I have Cu and there's only one of them. And then I have IO2, but I have two of them. So I know some of you might want to write this I2O4 because we have two, so that would add everything together. But if you look on your ion sheet, your polyatomic ion sheet, you never see I2O4. That's not an ion that we talk about. It's always just I2. So instead of writing I2O4, I'm going to put IO2. But now I want to make sure I tell you I have twice as many, which means that I need to put two sets or put parentheses with a 2 telling me there's two sets of IO2 present. Any questions on that one? All right, then the next one. Before we get into the next one, I do want to just make a note that if we have polyatomics, if they're present in our formula, we need to see 3 or more elements. So if you can only count 2 elements, there are no polyatomics present. If you count 3, 4, that means there are polyatomic ions present, and we need to figure out which ones are present. So if we look at this one, let's first count how many elements do we have? How many different elements?
2.
We have how many? You say it again?
2.
2. Careful, not just 2.
Oh wait, 3.
We have 3 because calcium, that is a lowercase a, so that's 1. N by itself is another one, and O by itself is another element. So we have 3, which means there is a polyatomic ion present. Those parentheses actually make it quite simple to find our polyatomic ion, because if it's all put together, so if we have all of it in a parenthesis, that automatically tells us this right here is our polyatomic ion, which makes our life really simple. The first thing we need to figure out is Ca. What element is that?
Calcium.
Calcium. And NO3, what element is that? Or what polyatomic ion is that?
Nitrite.
You said nitrite or nitrate?
Nitrite. Oh wait, nitrate.
Nitrate is the correct one. NO3 is nitrate, and O2 is going to be nitrite. Which means we're done. This is our answer. Not too bad, right? Let's try the next one together. How many elements do you see here?
3.
We have 3 again, N, H, and Cl. Now, this one makes it a little bit more challenging because there's no parenthesis. We do need to figure out where our polyatomic ion is. So it can either be NH4 or it can be H4Cl. So we need to determine which one it's going to be. So let's look at our polyatomic ion sheet. Let's see if we can find it anywhere. So let's look for NH4 or let's look for H4Cl and tell me when you see it.
Ammonium.
Perfect. Ammonium. It's on our cation side. And if you notice, this is our only polyatomic ion that is a cation or a positively charged ion. The rest of our polyatomics are our anions, our negatively charged ions. So that is our biggest challenge, is to figure that out. So if you ever see NH4, you need to know that's ammonium. It's on that left side. So it goes first in our cation anion combination. So I'm going to get rid of this, and we know that this NH4 is ammonium, which means the Cl is what element?
Chloride.
Chloride. Perfect. We have to remember that our ending of our second element does change because it's an element from the periodic table, not just an element or an ion from our polyatomic ion sheet. All right, just like before, you guys have the third one, the Al2SO43. Identify if we have polyatomic ions and then determine that name. I'll pull up the ion sheet again. All right, ladies and gentlemen, let's go through that last one. Which one of these is our polyatomic?
SO4.
SO4 is the polyatomic, and what polyatomic is it?
Sulfate.
Sulfate. What is Al?
Aluminum.
Do we need Roman numerals?
No.
Nope, so we are done.